Hello, welcome back. Now we are starting a new discussion on new topic. So the new topic is the relative performance evaluation. So as you know, we are following the Nobel Prize document on contract theory. So what was the first topic that is discussed in the document? Let's just go to this document. So you know you are supposed to read this document, right? So I assume you have read this document, and probably you had some difficulty understanding everything written in the document. And the first topic that is discussed in the document is the tension between insurance and incentive. So I encourage you to go back to this document and read this part at least, and check your understanding on this topic, the tension between insurance and incentive. After after you have taken my lecture, I hope your understanding is much improved. So you now read this document at much easy. Uh, so so the first topic was the tension between insurance and incentives, and then the next one is the paying for performance. What does paying for performance means? So it simply means the incentive contract, right? So the you know from very early days, people have understood that the importance of incentive incentive schemes, and but still at the early times they didn't know how to design the optimal contract, uh, optimal incentive contract. So later in 1970s, 1979, these two guys, Ben Holmstrom and Stuart Chavelle, came up with this idea of the informativeness principle. Okay, informativeness principle. That's the topic that I want to discuss today, and probably for a couple of days. Okay. So, and that's the topic that will be discussed in this lecture. So, what is this informativeness principle? It simply means that an optimal optimal contract, optimal incentive contract, should link payment to all outcomes that can potentially provide information about actions that have been taken. So, we have seen this. We have seen an incentive contract. We have seen an optimal incentive contract, and there we could see the importance of information. And when the size of noise is very large, then you cannot give very strong incentive. If size of noise is small, then you can give a strong incentive, etc., etc. So yeah, probably we have seen something similar, right? So the optimal contract should link payment to the outcome, which which provides some information about the action of the agent. But this is something more. There is something more in this. Okay, so we have to focus on this term, this word, potentially, right? So all outcomes. So an optimal contract should link payment to all outcomes that can potentially provide information. So what that means is, in the optimal contract, there must be something more. The optimal contract must be contingent on many other things too. Not only just performance measure like the revenue or the exam scores. They are really important information. They provide really important information. They are really important measures, but still we cannot say those contracts which only based on the performance measures of the specific agent is not optimal, because there are other things, other measures, other variables which may show the which may provide more information on the agent's action. Okay, so suppose, let's consider this example. Suppose a manager influences her own firm's share price, but not the share prices of other firms. Okay, so a manager here, the manager is the agent and the investors are the principal. So the manager is an agent, and this agent can influence her own firm's share price. So the share price is the performance measure. Okay, so the manager is the agent and the share price is the performance measure, like X. Okay, but not the share prices of other firms. But still, we may have to consider the share prices of other firms when we write down the optimal contract, optimal incentive contract. We have to think about the share prices of the other firms as well. So that's the lesson that we can derive from this discussion. So why is that? Since share prices reflect other factors in the economy outside the manager's control, for example, the business cycles, like the people's tendency to consume, tendency to invest, everything else, right? So the share prices reflect lots of things, not just the manager's effort, but also all the other things that happens in economy. So simply linking compensation to the firm's share price will reward the manager for good luck and punish her bad luck. So there must be some noises, there must be some random factors, but that's not ideal, right? That's not what we want to do. So it is better to link the manager's pay to her firm's share price relative to those of other similar firms, such as those in the same industry. So this is the idea of relative performance evaluation, and it's basically saying that when you write down a contract, if you want to write down an optimal contract, then you have to use something similar to relative performance evaluation, because others' performance, like the other firms' share prices, have some information about the economy itself, which is like good luck or bad lucks. Okay, so by controlling for those information, you can reduce the variance of the noise. So what happens if you reduce the variance of the noise? Then you can improve the contract by giving a better incentive, maybe by giving a stronger incentive, right? So we are still talking about this, the trade-off between insurance and incentive, but we add more elements in it. Okay, so so to understand this informativeness principle, we have to first understand the basic principle agent model and the tension between insurance and incentive, and then and then we add more information in the contract. That's how we maximize. So that's how we optimize the contract. Okay, so the optimal contract must be contingent on all possible, all available information, which potentially provide information about the agent's effort. Okay, so that's the informativeness principle, and that's what we want to discuss in this lecture. So relative performance evaluation is you know what it is. So we have done it for a very long time in universities and in probably in other institutes, like maybe in high school as well. You see the rank of students, not just the absolute scores. Okay, so that's by looking at the ranking, the rank of the performance, you are basically applying the idea of relative performance evaluation. Okay, so then why is it important and why is it efficient? Why is it better than just looking at the absolute scores? Because the scores, for example, we are talking about an exam. So let's say we will not have an have the midterm exam, but let's say we have a midterm exam, then uh, and the difficulty of the midterm exam can vary a lot, right? So maybe in 1 year the midterm exam is very easy, and in another year midterm exam is difficult, and then we cannot compare those two. So to understand uh, who is really good at this course, who did really well in this course, you have to consider this difficulty of the exam, right? Because if if, if let's say your score is 50, let's say, then maybe you did so this number 50 doesn't give much information about your effort and your talent, because maybe if the exam was really difficult, then 50 maybe is really high score, right? Maybe 50 is the highest score in the class. That is possible if the exam was really difficult. On the other hand, 50 could be really a low score if the exam was very easy. So this this absolute this number 50 doesn't tell much about the effort or talent of the student, because we have to take into account the difficulty of the exams. But if you use the relative performance evaluation, like if you just look at the rank of students, then probably we can say that, okay, this student was on the top 5% in the class, so this student must be really talented, or this student must be studying really hard. Okay, so that's the benefit of using relative performance evaluation, right? And in more theoretical side, we will have to think about the risk as well. So let's just read this what's written in the slide. Okay, so when a common unobservable factor affects the performances of two or more workers, an employer can design a better contract according to which the compensation is based on the relative performance, not the absolute performance. The reason is this. Recall that when both the principal and the agent are risk neutral, the second best outcome is the same as the first best in simple principal agent model, but when the agent is risk averse, the effort, the second best effort is strictly smaller than the first best effort, because a stronger incentive implies a larger risk to the agent. So this is what we saw in the previous discussion, right? So there is in the simple principal agent model, there is the tension between insurance and incentives. So when the principal can use RPE, relative performance evaluation, the principal can provide an implicit insurance to the agents, the workers, and thus can achieve a better outcome. So by comparing the performances of the agent, so the principal can basically eliminate the common unobservable factor. Okay, so that's the key. So by comparing the performance measures of the two agents, the principal can eliminate the common factor, common unobservable factor, like the difficulty of the exam or the business cycle, something that affects to both performance measures. Okay, so by eliminating those random factors, the principal can provide a better insurance. So the principal provides better insurance. That means the agents care less about the risk, which means now the principal can provide better incentives as well. So that's how the principal improve the efficiency in writing a contract. Okay, so that's the basic story, and let's look at the details. So we start from this single agent model, which is exactly same with the example 2 in the basic principal agent model. So I'm not going to explain this model in detail, but I just quickly review what this model is saying. So the performance measure is X, which is sum of effort and noise, epsilon, and noise follows normal distribution, and the agent's payoff is the what the Kara utility function. So agent's utility function is Kara utility function. So the agent is risk averse, and cost function at the bottom, cost function is a quadratic function. And we are considering a linear contract, so the wage is linear in X, so T plus S times X. T is fixed payment, S is the marginal payment, and the principal's utility is linear, so the principal is maximizing just expected profit, X minus W. X is the revenue, W is the cost, so X minus W is the profit. And so, you know, after some math, we have this, we simplify the agent's problem into this. So the agents just maximize this quadratic utility function, and then we derive the optimal effort, and the principal's payoff is just to maximize expected profit subject to the IR constraint and IC constraint, right? And when you solve this problem, you get this solution. So the solution it looks a bit complicated, but we'll see very soon that this is actually very simple, relatively, right? So we will see much more complicated solution in this model with two agents. So we have two workers. So let's imagine there is a team, but they don't work together. I mean, they are in a team of, let's say, salespersons. So they work separately, okay? But their performance is affected by some same factor, like the difficulty of the exam or the some movement of the macroeconomy. Okay. So that idea is captured in this assumption. So performance is denoted by this xi. So now we have two agents. So this index I is for agent I. So xi is the performance of agent I. AI is agent I's effort, and epsilon I and epsilon j are noises that follows normal distribution. And we'll assume that epsilon I and epsilon j are independent. And alpha here is it measures the size of the common factor. So if alpha is very large, that means there is a large common factor. And if alpha is small, that means there is not much. The common factor is very small. It is relatively unimportant. So let's consider an extreme case. So let's suppose alpha is 0. That means there is no common factor. So that means the performance is independently observed. Performance is independently measured. Excuse me. If alpha is not 0, that means performances of the two workers are correlated, right? So if alpha is positive, that means the performance measure is positively correlated. If alpha is negative, that means the performance measures are negatively correlated. we'll consider the case with negative alpha, but for most of time we will consider the case where alpha is positive, right? That makes more sense. Like, there is some common factor which affects the performance of both workers, both agents, then that factor is likely to affect to the agents in the same way, right? So that means there must be some positive correlation between the two workers' performance measures. So we consider two cases, like alpha is 0 or alpha is positive, right? So if alpha is 0, that means the performance is independently observed, and if alpha is positive, that means there is some positive correlation between agent I's performance measure and agent J's performance measure. Okay? So, and we consider a linear contract as before. So Wi is the wage of agent I, uh, and it looks like this. So Ti plus Si times Xi plus Ri times Xj. So previously we didn't have this Ri times Xj. So what is Xj? Xj is the performance of agent J. So my wage depends not only on my performance, but also on others' performance. So that's the idea. Okay. So the if Ri is 0, that means this contract is independent from each other. So we have two workers, so two contracts. But if Ri is 0, that means these two contracts are independent. So it is the same to the contract that we considered in the previous discussion on the basic principal agent model. But if Ri is not 0, that means there is some sort of relative performance evaluation. So it is likely that Ri is negative, right? So then if Ri is negative, that means if another person, let's say my rival, no, it's not really my rival, but if another worker does really well, then my wage will decline, right? What's the rationale for that? My wage will decrease when my teammate or another worker's performance is very good. The reason is it's likely that another worker's performance is very good because of some common random factor. So, and we want to eliminate the random factor by subtracting from one measure to another. Okay. So that will be the idea. That will be the case, and we'll see that very soon. And note that the variance of the wage looks like this. So the variance of wage is this. So wage has three terms, right? So first term is fixed term T. The second term is S times Xi, and the third term is R times Xj. So T is fixed term, so we can ignore it when you calculate the variance. But the second term is random because S times Xi and Xi is random. In Xi there is epsilon I plus alpha times epsilon j. So the from this S times Xi we have this S times epsilon I plus alpha times epsilon j, plus we have the variance from the third term, the last term, right? So Ri times R epsilon j plus alpha times epsilon I. So this is the variance of the wage, and it can be written like this. So it's sigma squared times S1 plus alpha times R1 squared plus R1 plus alpha times S1 squared, right? Uh, this is very easy to derive, and if you are not sure, then you can go back to your statistics notebook or textbooks to see this will be the case. And because epsilon 1 and epsilon 2 are independent, there is no correlation terms. That's uh, one thing you can notice here. So the agent's problem can be written like this. So the agent problem, agent here actually an agent, because there are two agents, right? So this is the agent 1's problem. So if the agent 1 accepts the offer, then the agent 1's the effort decision can be written like this. So the T1 plus S1 times A plus R1 times A2 minus the effort cost minus the distributivity from the variation, the distributivity from the risk. Okay, uh, so this is the agent's utility maximization problem, and you can see that A2 appears in the in this expected utility, but it doesn't matter because A2 is a choice variable of the agent 2. So when the agent 1 maximizes the utility, agent 1 regard A2 as a constant. So A2 can be ignored, right? And then we just maximize this objective function with respect to A. And then we'll have this optimal effort, which is what? Which is same as before, right? So you differentiate this objective function with respect to A, then you get S1 minus C times A, right? So the optimal effort A will be S1 over C. It's same as before. Okay? So even if you use this relative performance evaluation, the effort, the optimal effort only depends on the marginal payment S. Okay? So it doesn't depend on T nor R. Okay? So that's the optimal effort. And the principles problem can be written like this. So we have two agents. So ideally, if you just play very straightforward, then you are supposed to write the expected profit from agent 1 plus expected profit from agent 2. But here I just wrote expected profit from agent 1 only. The reason is agent 1 and agent 2 are symmetric. They are identical. So we don't have to consider the two agents. So just considering just one agent is enough. So if you want to maximize the expected profit from the two agents, then we'll have more choice variables, right? So here the choice variables are T1, S1, R1, but if you consider two agents, then we'll have three more choice variables, T2, S2, R2, but we don't have to because they are symmetric, and it will be optimal to set the to give a symmetric contract to these two workers. So in equilibrium, at optimum, T1 must be same with T2, S1 must be same with S2, and R1 must be same with R2. So that's something that we already know, right? because the workers are symmetric, they are identical in every aspect. So the optimal contract for those two must be symmetric, identical. So T1 must be the same unit T2, S2 must be the same unit S2, etc. So that's why we just consider just x1 minus w1, ignoring the other terms like x2 minus w2. Okay. So we have this IR constraint and the IC constraint, and then we solve this problem. Then we'll have this solution. Okay. So it's much more complicated, but we can still see some interesting things, like you can still notice the resemblance of the solutions, like this solution and this solution, right? So how do we compare this solution to this solution? It's kind of easy, right? So if alpha is 0, so let's suppose alpha is 0. If alpha is 0, then this A1 becomes 1 over C times 1 plus eta times C times sigma squared times 1. That's basically, oops, sorry about that, this. So what does that mean? So if alpha is 0, that means the two performance measures are independently observed. What that means is, if there is no common factor, when there is no unobserved common factor, the optimal relative performance evaluation is no relative performance evaluation. Okay, so if everything is random, purely random, so there is no correlation between the performance measures, then we don't use relative performance evaluation. In other words, the reason why the relative performance evaluation is good is that it can take care of this unobserved common factor. In other words, the relative performance evaluation is good only when there is unobserved common factor. So if there is an unobserved common factor, then there is no reason to use the relative performance evaluation. Okay. So if alpha is 0, so if there is no unobserved common factor, then we just use the contract that we derived in the previous discussion. Okay. So it looks complicated, but you can see the resemblance, and still we can understand, we can try to understand this solution. And I know this looks really monstrous, this looks really ugly, and it's not easy to derive this solution from the from the problem. So in exams, I usually don't ask. Actually, I have never asked to solve this problem to derive this solution. So don't worry too much about the math. I usually don't ask math problems if it is really complicated, because this is not algebra course. This is a construct and organization theory course. So I want to emphasize the intuitions, the logics, the economics, not the math, not the algebra. Okay. Okay. let's try to understand the result. So what is that? So R1 looks like this. R1 equals minus 2 alpha over 1 plus alpha squared times S1. So and S1 is positive, right? S1 is positive. So what this means is R1 is negative if alpha is positive. So if there is positive correlation between the between the the performance measures, then R1 must be negative. So that's what we expected, right? So what that means is when one agent performs well, then the other agent has to be penalized. Okay, so if my friend does really well, then I will be penalized. So that's basically the idea. That's the idea of relative performance evaluation. And most people do not like this idea because it's not humane. Uh, it encourages too much competition. So most people do not like this idea. But I want to say that still this is better than just absolute evaluation. This is better than focusing on the absolute scores. Relative performance evaluation is better. Why is that? Because it can take care of the unobserved factor, unobserved randomness. Okay, if there is some common factor, you can take care of it. So one agent will be penalized if the other agent performs well. By the same token, one has to be rewarded when the other does worse, when the other does really poorly. Okay, so by doing so, the principal can reduces the agent's exposure to a common shock, common unobserved factor, and thus reduce the variance. Alright, there was some technical problem, so anyway, I think it's been taken care of. So where are we? So by doing so, the principal can reduces the agent's the worker's exposure to a common shock, and thus reduces the variance of the wage. So by reducing this variance, the principal basically providing a better insurance to the agent. So, but because the principal is providing a better insurance, the agent is more willing to take the offer from the principal. So the principal now can have a room to increase the strength of incentive. So now the principal can give a stronger incentive to the workers as well. Okay, that's what's happening here. So if the let's consider these two extreme cases. So first, if alpha is 0, then the contract, the optimal contract, boils down to the single agent contract, individual contract. Okay, so that's one thing that we can observe from the by just looking at the solution in the previous slide. And if alpha is 1, then what? If alpha is 1, then you can see that S is 1. Sorry, S1 is 1. So what is S1? What does this S1 equals 1 mean? So it means the incentive is very strong. So incentive is the full incentive. Okay, and in that case, R1 must be minus 1. So R1 is minus 1 and S1 is 1. So that will be the case if alpha is 1. So what that means is it is optimal. So if alpha is 1, then it is optimal to give a full incentive, and at the same time you set R1 equals to negative 1. So it's like full relative performance evaluation. And in that case, not too surprisingly, A1 is 1 over C, which is the first best effort level. So what it means is when alpha is 1, the first best effort level is uh, achieved. So the first best efficiency is achieved. So what about the risk? So in so to talk about the first best, we have to think about two things, right? So the first one is the incentive, the second one is risk sharing. So what about the risk sharing? So is the risk sharing optimal in this case? The answer is yes. So let's just look at this. So the agent 1's performance measure x1 is a1 plus epsilon 1 plus alpha times epsilon 2, and x2 is a2 plus epsilon 2 plus alpha times epsilon 1. So if alpha is 1, so what happens? If alpha is 1, then the noise becomes the same. So the noise in x1 becomes epsilon 1 plus epsilon 2, and noise in x2 becomes epsilon 2 plus epsilon 1. So if you subtract x2 from x1, then the noises cancel out, and what's left is the difference in the effort. So what that means is we can completely eliminate the noise if alpha is 1. If alpha is 1, then the noise is just common, right? So the common unobserved factor explains everything. I mean the common unobserved factor is the noise. So in that case, by subtracting one from the other, we can recover the difference in effort. So what that means is by eliminating this noise, we can eliminate the asymmetric information problem in a sense, right? So you may think that okay, so we can recover the difference in effort by comparing the performance measures. By subtracting x2 from x1, we can recover the difference in effort, but that doesn't mean that effort itself is recovered. So maybe we want to think about the case that maybe we want to recover just A1 alone or A2 alone. Only in that case, maybe we want to say there is no asymmetric information problem. But I still want to say that in this case, there is no asymmetric information problem in equilibrium. Okay, so in equilibrium, one player has no incentive to deviate from the optimal. So what does that mean? So let's say A2 is given by A2 star, the optimal the equilibrium effort level. And this equilibrium effort level is what? Equilibrium effort level is 1 over C. It's a known number, so you know what it is. So you know A2 is 1 over C. Then if you observe any difference in x1 and x2, that will mean that A1 deviates. Okay, so let's imagine you are worker 1. So you are worker 1, and you know that in equilibrium, worker 2 will play the equilibrium. Okay, you are the worker 1, and you know that worker 2 will exert exactly 1 over C. Okay, you know that A2 is 1 over C, and you also know that the principal know the principal knows that A2 is 1 over C, and you are thinking about deviation. You are thinking whether you can improve your situation by deviating from 1 over C. And if you deviate, then you will be noticed directly because there is no noise. Okay, so if x1 minus x2 is not 0, that means one player deviates from the equilibrium, and that player will be punished. Okay, so in that sense, in equilibrium, there is no asymmetric information problem. So this difference is enough. So this difference is enough to notice any deviation from the equilibrium. So what that means is it's basically the full information benchmark case. So the full information benchmark is unrealistic ideal benchmark, but here this is something we can imagine, right? So if there is some common unobserved factor, then we can eliminate, or at least we can reduce the variance of noise quite drastically. Then we can achieve something similar to the first best. So, and also I want you to notice that the wage is non-random, right? So the wage looks like t plus x1 minus x2, right? So let's go back to this. So if alpha look at the bottom. So when alpha is 1, S1 is 1 and R1 is minus 1. That means wage is T1 plus X1 minus X2. What is X1 minus X2? X1 minus X2 is just A1 minus A2. There is no epsilon. So the wage is non-random. So what that means is the workers do not take any risk. So risk sharing is optimal too. So the risk sharing is in the way that the principal takes all the risk and the workers do not take any risk. So it's basically the first best outcome, the first best situation. Okay. Then if alpha is smaller than 1, the result is not as good as the case with alpha equals 1, but still we can reduce the variance of the wage quite a bit. What that means is the principal can provide a better insurance, which in that case the principal can provide a stronger incentive as well. So overall the efficiency will be improved. Okay, that's how we write an optimal contract, optimal incentive contract, and from this we can learn what is informativeness principle mean. Okay, all right. That's for today. Thanks and bye.